Hello friends, welcome to the 21st class of this course. In the last class, we talked about the conservation principles and how they are related to the symmetry properties of the system. There we learned about the canonical momentum and the cyclic coordinates. So one of the most important result was that if a coordinate is invariant under translation, or in other words, if the coordinate is symmetric, then the corresponding conjugate momentum of the coordinate will be conserved. So this is how the symmetry properties are related to the conservation principle. So by looking at just the symmetry of the coordinate, we can draw conclusion about the conservation of its canonical momentum. In this class, we will talk about the energy function and the conservation of energy. So let's say we have a Lagrangian L, which is a function of Q, which is the generalized coordinate, Q dot, and T. So in that case, dl dt will be sum over I del L del Qi dQi dt plus sum over I del L del Qj dQj dt plus del L del T. We can also write it like sum over I del L del Qi dot plus sum over I del L del Qj dot, del Qi del Qi dot dt. So this is del L del Qi dot times del dQi dot dt. So it is del Qi dot, and dQi dot dt is Q double dot, Qi double dot plus del L del T. Let's call it equation 1. Now from Lagrange's equations of motion, we have ddt of del L del Qi dot equals to del L del Qi. We are considering that there are no constraints in the system. So if there are constraints, so we will talk about that kind of system later. So let's call it equation 2. And we will put this expression of del L del Qi in equation 1. So here in place of del L del Qi, we will put this value, which is ddt of del L del Qi dot. Then equation 1 will become, so equation 1, it will become dl dt equals to, so if we put the value of del L del Qi from equation 2 in equation 1, so it will be sum over I and we have ddt of del L del Qi dot, ddt of del L del Qi dot times Qi dot plus sum over I del L del Qi dot times Qi double dot, del L del Qi dot times, let's write it ddt of Qi dot plus del L del T. Then this term will be, so these two terms, it will be sum over I ddt of del L del Qi dot times Qi dot plus del L del T. So if we take the derivative, then first this term is intact and derivative of this del L del Qi dot, which is the first term of this expression. And then the second term will be del L del Qi dot. So this term is intact and the derivative is on this term. So which is dt of Qi dot. And we can also put this time derivative outside of summation. Qi dot plus del L del T. So in that case, if we take this dl dt in the right hand side, then it will be 0 equals to ddt of sum over I Qi dot del L del Qi dot minus L plus del L del T. So this term, this minus L, it will be dl dt minus dl dt, and this term will come from this left hand side. We can also write it like ddt of sum over I Qi dot del L del Qi dot minus L equals to minus del L del T. Let's call it equation 3. Now this term inside this third bracket, this sum over I Qi dot times del L del Qi dot minus L, this term is called the energy function, which is defined by small h. So it's a function of Qi's. So let's say Q1, Q2 dot 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 Qn, comma Qi dots, that means Q1 dot Q2 dot, comma dot 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 Qn dot, comma T. So it's a function of generalized coordinate, generalized velocity and time. This function is called the energy function. So if you look at this expression, actually this term, this expression, it is same as the Hamiltonian expression of Hamiltonian of the system. So Hamiltonian is written by plus h, but we are not calling it Hamiltonian, though the expression is same, but we are not calling it Hamiltonian. It's because we are writing this energy function as a function of generalized coordinate generalized velocity and time. In case of Hamiltonian, the functional form or the expression will be the same, but there we will write it in terms of generalized coordinate and its conjugate momentum. So that's the difference. I mean, we are choosing just different variables to write it. Otherwise, the expression is same. So we will talk about the Hamiltonian at the end. So for the time being, let's concentrate on equation 3. So then this equation 3 will become dH dt equals to minus del L del T. So from this expression or from this equation, let's call it equation 4, we can conclude that if the Lagrangian is, or if the Lagrangian has no explicit dependence on time, then the energy function H is conserved. So if this Lagrangian has no explicit dependence on time, in that case the del L del T will be 0. So that means dH dt is 0, which means H is a constant quantity. So H is a constant of motion, or in other words, H is conserved. So that's the conservation principle of the energy function. So the energy function is conserved when the Lagrangian has no explicit time dependence. So now a natural question may arise, like is the energy function, it is same as the mechanical energy of the system? Is it the same as total mechanical energy of the system? The answer is, it is not in general. Under certain circumstances, the energy function will be equal to the total mechanical energy of the system. So let's see under what condition the energy function will be the will give the total mechanical energy. So in one of our previous classes, we learned that the kinetic energy, which is denoted by T, it can be written into three parts: T0 plus T1 plus T2. So where T0, it has no dependence on generalized velocity, which is q dot. T1, it is linear or first order in generalized velocity. So first order in generalized velocity. And it is quadratic in generalized velocity. So for our Lagrangian also, so for most of the problems, we encounter, the Lagrangian also the Lagrangian can also be broken into three such parts. So which is L, which is a function of Q dot and T. It can be written as L0, which is a function of only Q and T, plus L1, which is a function of Q dot and T, but it is first order in Q dot, plus L2 Q dot T, which is second order in Q dot. This is second order or quadratic in Q dot. This is first order or linear in Q dot. And it is zeroth order, or it has no dependence, no Q dot dependence. So no Q dot dependence. So now there is a theorem called the Euler's theorem, which says if f is a homogeneous function of degree n in variable xi, then in f equals to sum over I xi del f del xi. So this is the Euler's theorem. So if f is a function which is of degree n in variable xi, in that case del f del xi times xi, and sum over all I, it will be n times f, where n is the degree of that function in variable xi. So in that case, for our Lagrangian, we can write sum over I qi dot del L0 del qi dot equals to 0, because L0, it has no dependence on qi dot. That means its degree n is equal to 0 in xi dot, in qi dot. So in that case, from this Euler's theorem, we can write it like n times, which is n is 0 here for L0, n times L0, and which is 0. We can also write sum over I qi dot times del L1 del qi dot. It is equal to L1, because L1 is first order in qi dot. So that means here the n is 1. So from this Euler's theorem, we can write this quantity, this expression equals to L1, 1 times L1. And we can write sum over I qi dot del L2 del qi dot equals to 2 times L2, because here L2 is second order in Qi dot. So n is equal to 2. In that case, from this Euler's theorem, we can write it. We can write this expression equals to twice L2. So in that case, our energy function H equals to sum over I Qi dot del L del Qi dot minus L equals to sum over I Qi dot del L0 del Qi dot plus sum over I Qi dot del L1 del Qi dot plus sum over I Qi dot del L2 del Qi dot minus L. So L is L0 plus L1 plus L2. That's how we got this expression. So in that case, this first term, it is 0. You already derived it, that the second term is L1. This is the second term. And the third term, it is twice L2. So we can write 0 plus L1 plus twice L2. And the third term, L, this minus L, this L can be written as L0 plus L1 plus L2. And with this minus sign in front, it will be minus L0 minus L1 minus L2. So in that case, our energy function will be this L1 and this L1 will cancel, and we will get, so there is 2 L2 minus 1 L2, which is we are only left with 1 L2 and minus L0. So it will be L2 minus L0. Let's call it equation 5. So our energy function is L2 minus L0. Sorry, it is L0. Now, we will use two conditions. So condition 1, if the transformation equations defining the generalized coordinates that means the transformation equations defining the generalized coordinate means equations like this. It is from, let's say, Ri, how Ri depends on this generalized coordinate dot 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 Qn. So Qn comma, let's say Q1 dot comma Q2 dot comma dot 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 Qn dot comma T. So these kind of equations. So by saying transformation equations, we mean these kind of equations. So these are the transformation equations that defines the generalized coordinate in terms of the given coordinate Ri's. So if these transformation equations do not involve time explicitly, do not involve time explicitly, that means if there is no t here, so if this t is not there, if this t is not there, explicit time dependence, it is not there. That means if del r del t equals to 0, then we have, so then this kinetic energy, so it was m0 plus, so m0 is uh, m0 has no dependence in generalized velocity. Then some over I mi qi dot plus some over j k half m j k qj dot qk dot. So this is the t0 term, this is the t1 term, which is linear in generalized velocity, that is qi dot, and this is the quadratic in generalized velocity, this is t2. And this m0, it is, so this m0 is sum over I half mi del ri del t square. This mi is sum over I mi del ri del t times del ri del qj. Sorry, this is the sum over j, and this is del ri del qi, and m jk, it's equal to sum over I mi del ri del qj times del ri del qk. So in that case, if this transformation equations has no explicit time dependence, that is if del r del t is 0, this r has no explicit time dependence, then m0 will be 0. So it will be 0 because there is del r del t, and which is 0, and mi, it will also be 0. So that means this t1 and t0, this is the t0, this is t1, and this is t2. So t0 and t1 both will be 0 if these transformation equations have no explicit time dependence. So then we will have t equals to t2. If del ri del t equals to 0. This is condition 1, and condition 2 is if the potential does not depend on generalized velocity. Q dot. So if the potential does not depend on generalized velocity, in that case, the L2 equals to T2, and L0 equals to minus V. So if the potential does not depend on generalized velocity, so then potential has only I mean, there is no dependence of generalized velocity, so it will contribute only on L0. And then in our Lagrangian, there will be only T2 term. And okay, so if the potential does not depend on generalized velocity, then L0 will be T0 minus V, L2 will be T2, and L1 will be T1. So these L1 and L2, L1 is linear in generalized velocity, and L2 is quadratic in generalized velocity. So there will only be kinetic energies, because potential energy is independent of generalized velocity. So potential energy will only come in this expression of L0. So now if we combine these two conditions, condition 1 and 2, so if condition 1 and 2 both are satisfied, now if condition 1 and condition 2 both are satisfied, then we have L2 is equal to T2. This is because of condition 2, and because of condition 1, this T2 is basically the total kinetic energy, right? So we have L2 equal to T2 equal to T. L1 equals to T1 because of condition 2, and because of condition 1, since del R del T is 0, we have this T1 equals to 0, right? So this Mi equals to 0, it means T1 equals to 0. And our L0, which is because of equation 2, which is T0 minus V, but because of condition 1, T0 is 0, right? Because M0 is 0 and M0 is basically equals to T0. So we have T0 is 0. So in that case, L0 will be minus V. So if these two conditions are satisfied, then L2 is total kinetic energy, L1 is 0, and L0 is negative of potential energy. So in that case, our Lagrangian will be, or in that case, our energy function will be H, which you already derived its expression from equation 5. We can write L2 minus L0. So L2 minus L0 from equation 5. Sorry, it is L0. L2 minus L0. This is from equation 5. So here we only consider that this Lagrangian, it can be divided into three parts, which is L0, L1, and L2. So in that case, our energy function will be, so L2 is total kinetic energy, and L0 is negative of total potential energy, and there is a minus sign, so it will be T plus V, which is the total mechanical energy. So it says that, so basically what we derived, it's a very important result. It says that the energy function will be the same as total mechanical energy of the system if condition 1 and condition 2 both are satisfied. That means if the transformation equations defining the generalized coordinate do not involve explicitly in time, and if the potential does not depend on generalized velocity. So if number 1, the transformation equations has no explicit time dependence, and number 2, the potential has no generalized velocity dependence. Under these two conditions, the energy function will be equal to the total mechanical energy. And moreover, if Lagrangian has no explicit time dependence, then this total mechanical energy which is E equals to T plus V will be conserved. So if Lagrangian has no explicit time dependence, then total mechanical energy will be conserved. This is because the energy function will be conserved if the Lagrangian has no explicit time dependence. That we already derived here. So now the question is, what happens if we have a dissipative system? For dissipative or non-conservative systems. So for non-conservative systems, the Lagrangian equation will look like, so this we already discussed in one of our previous classes, minus del L, so del Qj plus del F del Qj dot equals to 0. So where this curly F is the Rayleigh dissipation function. So it's a velocity dependent function. So in that case, we can write del L del Qj equals to ddt of del L del Qj dot plus del dissipation function del Qj dot. So then dl dt, which was sum over I del L del Qj dQj dt plus sum over I del L del Qj dot dQj dot dt plus del L del T. It will be sum over I ddt of del L del Qj dot dQj dt, or we can write it as Qj dot plus sum over I del L del Qj dot times dQj dot dt plus del L del T, and there is another function because of this dissipation, Rayleigh dissipation function. There is another term here, so which is plus sum over I del curly f del Qj dot times Qj dot. So this if dependency will come through this through the first term here. So in place of del L del Qj, we are writing this. So from the first two term, we can write. So in the left hand side, it is dl dt, and in the right hand side, the first two term will give me ddt of sum over I Qj dot del L del Qj dot plus del L del T plus sum over I Qj dot del dissipation function del Qj dot. Then we can write ddt of sum over I Qj dot del L del Q dot del Qj dot minus L equals to minus del L del T minus sum over I Qj dot del F del Qj dot. Which is ddt of H. So this is our energy function. So ddt of H equals to minus del L del T minus sum over I Qj dot del curly F del Qj dot. So now in general, this dissipation function, it is second order in generalized velocity. So in general, F is second order in Q dot. So then from the Euler's theorem, we can write sum over I Qj dot del F del Qj dot equals to twice curly F, twice dissipation function. So then we can write dH dt equals to minus del L del t minus twice curl df. Now if Lagrangian, if L is, so if L has no explicit dependence on time, if L has no explicit time dependence, then we have dh dt equals to minus twice the dissipation function, or we can write it like dissipation function equals to minus half dh dt. So it's a very important function. It's a very important relation. So we talked about this relation in one of our previous classes also, where we introduced this distribution function. So it says that the rate of change of energy of a system, the energy loss, so that is twice the distribution function. So that's the meaning of the distribution function, physical meaning of the distribution function. So if there is the dissipation function exists, in that case, the energy, it will not be conserved. The energy function will not be conserved. And the rate of the change of energy, it will be equal to twice of the dissipation function. Since we introduced the concept of energy function in the class, so let me give a brief introduction about the Hamiltonian. So the energy function was defined as energy function h, which is a function of generalized coordinate, generalized velocity, and time. It is defined like sum over I qi dot del L del qi dot minus L q dot t. So this energy function, it is a function of generalized coordinate, generalized velocity, and time. Now this del L del q I dot, it is the canonical momentum corresponding to qi coordinate. Right? So we already, in the last class, we already defined the canonical momentum. This del L del qi dot, it is the canonical momentum corresponding to the coordinate qi. So then we can write this del L del qi dot as pi. So in that case, this this expression will look like sum over I qi dot pi minus L q qi q dot comma t. So this expression we will call it Hamiltonian, denoted by h, if we write this expression using the variable q, p, and t. So we need to calculate this expression, and we need to replace the values of qi dots with the p, with the canonical momentum. So in that case, we will call this expression as Hamiltonian. So the functional form is same. It is just the variables we are representing it. So it is just the variables. For energy function, we are the variables are the generalized coordinate, the generalized velocity and time. And for Hamiltonian, we will express it in terms of generalized coordinate, the canonical momentum, and time. This is how we define our Hamiltonian. which is the expression of which is same as this energy function. And the Hamilton's equations of motion, they will look like qi dot equals to del h del pi and pi dot equals to del h del qi. So these two will be the Hamilton's equation of motion. We will talk about this Hamiltonian when we in great detail. In fact, we will talk about them when we will go to the Hamilton's equation of motion. So when we learn about there, we learn about the Hamiltonian, and we will solve a lot of problems on that topic. So that's all for today. Thank you.